Welcome back to Physics 142 online. We're now making the transition to the next part of the course where we're still treating the physics of waves, but we're going to focus now on the wave properties of light. This subject occupies 2 full chapters in our textbook, but we're going to treat them as one unified unit. And we'll start with some historical overview and definitions of the properties of light. The nature of light has been a matter of some debate among scientists over many centuries. So, rewinding to the 17th century, there were 2 prominent spokesmen for the opposing views of the day. Our friend Isaac Newton, whose name we've heard in other contexts, believed that light was a stream of tiny particles, which was suggested by a phenomenon that you might be familiar with if you're in a dark room and maybe you have a window and sunlight is coming through the window through little shades, the slits in some kind of shade. It appears that light is composed of a ray, a stream that travels in straight lines through the slits into a dark room. Christian Huygens, on the other hand, believed that light was a traveling wave, that it was more akin to a wave on a string, or the wave ripples that are sent out in a pond if you drop a rock into a pond. So these 2 views were opposing views, and Newton probably had the upper hand in the day because of his great prominence introducing the calculus and also the laws of motion. So, schematically, here's the big question. Was Newton right? Was light really a stream of particles, or was it more like a wave? And one of the difficulties, and one of the reasons why that question was hard to answer, was that if light really was a wave, as Huygens believed, it should have been possible to devise an experiment where you could see its wave properties, or where perhaps you could measure its wavelength. But that did not happen back in the day of Newton and Huygens, and the inability to detect the wave nature of light probably was another factor that counted in favor of Newton's theory, which was sometimes called the corpuscular theory, thinking of light as a collection of tiny corpuscles. So what are the properties of light that were known to people back in Newton's day? Well, probably the value wasn't known very precisely, but not too long after Newton's time, the first crude measurements of the speed of light were made, and our modern value for the speed of light in a vacuum is used. The symbol c is what we use for this, and it's about 3 times 10 to the 8th meters per second. It turns out that the speed of light in a vacuum is a fundamental parameter, a constant of nature, and so it has fundamental significance in the history of physics and in our understanding of the properties of the universe. Now, in a medium, a transparent medium through which light can propagate, its velocity is actually reduced. Experimentally, we can see that the value is not 3 times 10 to the 8th, but is actually somewhat smaller. And the factor by which the speed of light decreases is called the index of refraction, and we give the symbol n to this. And you can see some typical values. Of course, in a vacuum, n by definition then would be 1 because the speed v would be equal to c. In air actually is not a vacuum. It has molecules in it, and so there's some very small interaction of the light with those molecules that slows it down a tiny bit. But then in other substances like water and glass, you can see that the slowdown is rather significant. The visible spectrum, by the way, the wavelengths of light that human eyes respond to, is roughly between the wavelengths of 400 nanometers and 700 nanometers. And a nanometer, a nano is 10 to the minus 9, so this is 400 times 10 to the minus 9 meters, or 4 times 10 to the minus 7 meters. So that's the visible spectrum, and you might have problems occasionally where they will ask you information about where you need to know these limits within the visible spectrum, so be aware of that. Now, in about a century and a half after Newton was born, there was a very famous experiment that was done by an English scientist named Thomas Young, and his work caused there to be a new ray of light dawn on the question that Newton and Huygens had argued about. So Thomas Young's experiment, which is also sometimes called the double-slit experiment, very much resolved this question once and for all. Young was trained as a medical doctor, but back in those days it was very easy to make contributions in more than one area of science, and so he contributed significant things to our understanding of color perception, the elasticity of solids, Young's modulus, which is a property of the elasticity of solids, that's named after him, and he even helped do some work that led to the deciphering of the Rosetta Stone. So Young's experiment qualitatively looks like this. There is a source of light where the light comes in from the left, from some kind of a source, and it's going to hit a screen in which there are two small holes. And S1 and S2 act like two different sources of light. So the light that comes through originally comes from the same source, and that means that the light, if it has a wave, it's coherent, so that the light has stable phase relationships, the light that comes from S1 and S2. It's monochromatic, it's got a single wavelength, and since they do come from the light that goes through S1 and S2 comes from the same source, we assume that the light, if it's a wave, right, it's going to start off in phase. And so what we want to do then is look at the pattern that's formed if we let the light go through these two slits. What do we see on a viewing screen a distance L away? And what we see, and this was what Young was able to do using some very, very small holes in the viewing screen, Young was able to show that what you see on the screen is not just a blob of light, as you might expect. If light's a stream of particles, you might expect to see a blob of bright light in front of each of the two slits on the screen. But what you see instead is a series of bright and dark regions on the screen that are referred to as interference fringes. So the bright region is where you would see a bright spot on the screen. The dark region is where you see nothing at all, an absence of light. And the way that this pattern repeats from bright to dark to bright to dark suggests that light really is a wave. Because the only way to make sense out of this is to imagine that there are special places on the screen where the light, being a wave, the light coming from the two sources, can interfere constructively at the very center, and then a small distance away that the light waves will interfere destructively, and we won't see any light at that point on the screen. So that's the basic gist of Young's experiment, and it gave very powerful evidence for the wave nature of light. It turned out that Huygens was right. Now, what do we do quantitatively if we want to understand the location of those points on the screen that show bright and dark spots? What we want to do is analyze at a point P on the screen. We want to look at the paths that the light has to travel to get from slit 1 and then from slit 2 to get to that point, and write down the conditions for the path difference between those two paths to cause either constructive or destructive interference. So here's how it goes. The difference between S2P and S1P is that extra distance that the light has to travel, and it's the distance right here. The extra distance, if we drop a perpendicular line, the dotted line here is a perpendicular line perpendicular to S2P. So if we drop that down there, it forms a right triangle, and the base of that triangle here is the extra distance that we call the path difference. And if D represents the spacing between the centers of the two slits, we can see from a little bit of trigonometry that the angle theta that tells us the location of point P with respect to the horizontal is also the same upper angle that we have in the small right triangle. And then trigonometry tells us that this path difference here is approximately equal to D times the sine of theta. So if this distance L is large compared to the separation distance between the slits, this is a very, very good approximation. It's only an approximation because the triangle that we have, if you make that perpendicular line, the two paths that from S1 to P and from this point here to P, those two distances aren't exactly the same. But if the angle theta is small, then they are very, very close to being the same, so that the true path difference is approximately equal to d sine theta. So what do we do with that? Well, we already know if you've got two waves that are in phase And if one of them has to travel a little bit further than the other one to reach a common point, we know what the condition is for that path difference to give us constructive and destructive interference. If the extra distance is equal to an integer multiple of the wavelengths, then the waves that started out in phase will still be in phase when they reach point P. And that's the condition for constructive interference. That's where we would see a bright fringe on the screen. By contrast, if that extra distance, which is d sine theta, were to be a half integer multiple of the wavelength, that would give destructive interference. So if d sine theta is equal to an integer m plus a half times lambda, that's where we see the position of dark fringes. So the theta value that you get will differ depending on whether you plug in m lambda for d sine theta or m plus a half lambda. M in these two equations is simply an integer. The lowest value of the integer could be 0, right? Because if m is equal to 0, then d sine theta equals lambda. That would be where the extra path difference would equal one exact wavelength. So, if m is equal to 0, then d sine theta is just equal to 0, which would mean the path difference is 0. That's what you would get at the central point on the screen. And of course, the angle value at that point would be 0, right? m equals 1 would give you the first location away from the center of the screen where the path difference would be equal to lambda itself. That would give us the first bright fringe moving away from the center of the screen. So here is a quick example. I'll set it up right now and then we'll finish it off in class. Typical homework problem. If monochromatic light with wavelength of 632.8 nanometers, and this value is appropriate for a certain kind of red laser light, if this kind of light is incident on two narrow slits that are 0.1 millimeter apart, how far apart will the bright fringes be on a viewing screen that's 1 meter away? So let's draw a picture, as we always have to do in these kinds of problems, showing the light coming in, wavelength lambda, the separation between the slits is d, and what we're going to do is figure out this distance. We'll call it y1 because it's the distance from the center of the screen to the m equals 1 bright fringe. That distance will be the separation distance between the two fringes. So what do? Well, we need to write down the condition for constructive interference where the bright fringes are located, right? And then if we can do that, that will tell us an equation that'll have the angle theta in it. And then if we know the angle theta, we will be able to figure out the distance y1 just using a little bit of simple trigonometry. So that's how to set that problem up, and we will finish it in class. I hope that this gives you a simple orientation to one of the most important experiments in the history of what was at the time 19th century physics, the very beginning of the 19th century, and the experiment that historically gave us the best evidence that light is actually composed of waves. I'll see you in class.